my presentation here. So we will be running through probably 30 minutes around. Saishri, can you please confirm that you are able to see my
Yes,
screen?
sir.
Right.
It is visible.
Thank
Yes.
you. So as it is already made clear, the course is meant to serve two purposes. First, at Unistring, we have quite a good number of openings. There are at least more than 10 plus openings. And Mrs. Neelima will be happy to hire them, give the offer letters, maybe in a month also, the moment couple of assignments are out and the HR team announces that these people are doing well. Even before the course announces, she'll be happy to give the offer letters to the people. That's the first reason. The second reason is we understand several other, other countries, other companies in our country who are struggling to get qualified manpower with the minimum skills to start their designs. So hopefully this course should meet that requirement as well. Some of you may get jobs in our company, but the remaining people, either international or national or, startup or, any company that you want to work in this area, we are sure this course, if you do active participation, you got no other option other than becoming a qualified engineer. Okay, the only thing that is needed, expected from you is a active participation. And another point I want to highlight here, even though this is offered as fully digital course, but the assignments and the the case studies are go so deep that you would be getting a real hands-on experience. Only thing is you should not miss these sessions in between, because once you go out of the track, it becomes difficult to bring back you along with the other colleagues. And one commitment that is needed from all of you, that unlike any course, this is not, you're not attending this course for any exams. No marks, no rank, and no JNTU certificate or nothing. This course you are appearing for your one of the most important reason that you want to get a job in this area, you want to build the skills, and you want to build a stable career and fast growing career with this background. So you need to demonstrate your commitment, sincerity in attending this course, all the sessions, doing assignments, honestly doing this. So there is no benefit that you get if you, what is it called, just copy paste from your friend assignments. It's okay, because by end of the day, our job offer, or for that matter, any company job offer, will only be with on a one-to-one interview by checking your skills. Even though if you manage to get a job, every company has got a probation period, training period. If you're not skilled enough, you'll be terminated. So unlike a one-time exam marks fulfilling purpose, this course is to build a lifelong stable career. If you like this area, maybe after attending couple of sessions, you may also take a decision, no sir, this course is not for me. Then also it's fair enough. At least you got a clarity, right, that this course is not for you. Then as you eliminate the options in career, you will land up into your desired career also faster manner. So for you to get a clarity, if you think this course, this kind of jobs are for you, you must demonstrate your commitment and sincerity. And I already clarified in one of my previous answering previous question, even though there are several basics are taught, you will get a job in a company if you are good at least one thing. So that will be a good starting point. Okay, so let me start. So I will be talking about mainly the skills that one would require to build if you want to get a job in this area. Of course, these skills you will get it once you complete this course. That is what we are trying to say. And I will also explain during my presentation from which engineering subject background these skills are connected directly or indirectly. So people who are inspired and who can spend some more time than what we are giving you content and what we are asking you to do, can go through those engineering subjects, at least those chapters which you find relevant, and revise them and make your concepts clear. Okay, so coming to, I'm sorry. So this, you broadly look at when you are joining into any PCB design company, broadly your PCB can be called as a digital or mixed signal PCB, or it's called an RF PCB. So if it is only digital PCB or only analog frequency, analog and low frequency PCBs and all, things are going to be very simple. The reason why things are going to be very simple is you think point A to point B, signal has to go, signal will go. Okay. Adjacent to this line, one more line is there, some data line is going. You expect that clock line is carrying clock line, data line is data line. They will go like that only. So everything at low frequency will work as you generally think is supposed to work. The moment you start coming out with a mixed signal design, the digital signals, analog signals together, you get first level of challenges. The moment you go to RF, where your frequencies go beyond some, 700 megahertz, 800 megahertz, like that 1 gigahertz, where your PCB track lengths are becoming comparable to a lambda by 4 or lambda by 8. Lambda, the wavelength. Okay, then it starts becoming little more tedious. So you will understand that no more a particular thing. I mean, like a line is not just behaving a line; it is acting as an antenna. It is coupling to another line. Then you would also be very much worried about what is called this impedance matching, which is also in your circuit basics you studied as a maximum power transfer theorem. Every stage to stage you have to match. Otherwise, from point A to point B, 4-5 blocks are in between. In a RF PCB, if impedance matching is not taken care, it does not pass through at all. So these are the things that fundamentally differ between an RF PCB and the other PCB category. So the simplest one is pure digital design. Then next to another simplest thing is a simple analog design, like an op-amp based buffer circuit or something. Little more complex thing is like in high frequency digital design or high frequency analog design. Further more challenging is basically high frequency digital analog mixed signal design. Even more challenging becomes the RF PCB design. And you can imagine if RF PCB and digital analog mixed are together, that is much more complicated. Okay. So maybe once we go to some case studies, probably Mrs. Neelima or her team members will share some of the real-time experiences. So a PCB is a simple, you design, manufacture, test, 3 simple steps. So we will talk more about each of them. Now we are coming to the skills. So let's look at this. Let's have a glance on all of them, and maybe by end of this 30 or 35-minute session, you should be able to get a fairly big picture, like whether you think this is relevant to you and you can pick up this, whether your subject basics are okay, or at least you are okay out of these 12 categories, some 5-6 categories you are okay, and remaining only you need a little more brush up and training and all. That picture you should get by end of this session. So first thing about terminology. So as I was mentioning that this course will be quite different than a classical course offered in the college. Okay, here the goal of this course is to teach you in a simpler manner, train you in a simpler manner, and make you productive immediately. Okay, so first thing that you are going to learn in the PCB is actually industry terminology, like what is schematic, what is Gerber, what is a drill file. Okay, so how it is relevant, what do you mean by FR4, what is Rogers, what is the material. So that's the first and foremost. If you learn that itself, you will be pretty confident. You can read any paper. Like I think whatever Mr. Srikanth has told and Amit ji has told, these terms and all, how they are becoming more relevant. The moment you understand the jargon in the industry, that's a first and foremost skill. Second thing, application requirement. I think during panel discussion, Mr. Srikanth has already emphasized on the application part. Everything will change from application to application. The standard will change. I mean, if you go deeper in understanding the application input-output requirements and packaging and its thermal management, all that is also very important. And mainly, if you see here, application requirement and reference design analysis. Here, I want to dwell something and tell you. See, reference design becomes so crucial in an industry that you will be basically 90% of the times you will be doing standard circuits only. Okay. Some of you who might have thought that, sir, I will design my own BGT, MOSFET, gate, current, voltage and all. I'll tell you 90% of the times you don't have to do that. Okay. So if you know why the circuit is like that, you are happy. But you just copy that circuit as it is from the reference design. That's why the reference designs are also given. Like for example, any component vendor, let's say any component manufacturer like Analog Devices, Texas Instruments, Xilinx, all these companies, when their components they give, let's say one amplifier, one filter, one switch, RF switch, they give you a reference design. Reference design implementing as it is, 90% of the cases your requirement is met with slight modification. Maybe the reference design is not talking about using both some SPI mode and also GPIO mode or something. The reference design might have done only for the GPIO mode where you put jumpers and test it. but your application requirement is to cater for both SPI mode and this. So like this, there will be some changes, but understanding a reference design, I would say your 90% of circuit design is over. So without knowing circuit design basics, 90% of designs can be done. This will be so simple in the industry. Understand that. But yes, you should know sometimes when you are changing, let's say there is a parallel capacitor is there, and in your impedance matching, that capacitance is not giving basically the required 50 ohm terminal impedance. You should know that capacitance you have to tweak, because the reference design is done for one type of PCB which is available only in the United States. And what is the PCB material available here? There is a slight variation in their epsilon R, which is a relative permittivity. You should know how to change that. But as a design, as a circuit, it is by and large available. Okay, that's a good news. Okay, third skill, you should be able to do circuit design. So sometimes let us say, you are taking one reference design from Xilinx, one reference design from Analog Devices, putting together, you should know the basics of circuit design, then only you'll be able to do it. Schematic creation. Schematic is nothing but a symbolic representation. You might have seen the BJT will look like this. Each one of you must have done some small laboratory course in multisim or KeyCAD or something. Schematic is nothing but those symbols you connect with them. It's pretty simple. It's very easy job. It's only your skill, your familiarity and the tool, associated concepts, okay, will actually be the back end. Otherwise, that connecting skill is a pretty easy skill. Okay. Okay. The category 4, the selection of the component and materials, because you have pretty much choices available. In fact, today engineering has become more complicated because of more choices are available. So if there is only one FR4 PCB, is there only one Rogers, is there? Actually, there is nothing to select also. Anyway, the point is you have a lot of components. Like let's say you want an RF pin diode switch, you have one type of switch that somebody calls that as a reflective switch, somebody calls it an absorbive switch. You should know what is reflective, what is absorbing type of thing, and you should select appropriately suitable to application. Then somebody say you have some Rogers one material with epsilon R of X value. Another company says I have a better material. Why it is better, you should know. Whether epsilon R being epsilon R being low or epsilon R being high, what is good? One has more advantage in terms of less losses. Other has more advantage in terms of it can store more energy, so more power dissipating capability. So all these concepts about the materials and components, yes, you do need knowledge of them. Library creation. Now, in any company like our company or any company where there are some considerable designers are there, we want to always reuse the design. So footprint library, design library like that. Layout design. Layout is nothing but you go to the top layer, bottom layer. Okay, this is a metal. This is I route like this. Then this is where I want to do some etching. This is a drill hole. I want to put a PTH component there. And this is actually a surface mount component. I want to put a pad. And like I want to route from the top layer to the bottom layer and again use some via and go to the inner layer. These are all called layout design. Power analysis and distribution. Yes, that's a more challenging thing in this one is anybody who does a PCB design, just like that, it won't work, especially in defense and aerospace. When it has to work from -20 to +55 degree, you should be, your thermal design has to be good. That's what one of the panel member also highlighted that. So thermal management and mechanical design. One is the power analysis and distribution. That is to identify the hot spots on your PCB. You have some PCB here, I am getting more heat, here I am getting more heat, here I am getting more heat. That is the first part. Then the second part is the thermal management. So now I am getting heat, here, what kind of heat sink I am supposed to give, what is the landing area, how much thermal contact is needed, what type of thermal paste I have to put between my surface of the chip and all. If you have some QFN kind of component in the QFN, at the bottom there is a special thermal relief is given. How do you design your PCB for that? So that is all one category of the knowledge and skill that you need. Then verification and design rule check, DRC. So see, ultimately when you are design, that's where I think somewhere when I joined the panel discussion, Mr. Srikanth is talking about, you should be understanding the DRC. You should be understanding the tool. See, if you understand the constraints by which a company can manufacture a PCB, and if you know those constraints, how to program in your tool, because tool is built for a generic usage, and globally the same tool people may be using, but the manufacturing facility that is in Bangalore and the manufacturing facility that is in Taiwan, both of them may have a different design rules. So adding the design rules and design constraints in your tool and being able to generate a manufacturable design is a fantastic skill. In fact, I suggested the course instructor, Dr. Vishnu, to pick up enough case studies only on the queries between our company employees and the PCB manufacturing companies and PCB assembling companies. Those queries and communication between them through the mail will be actually taken up as a case study to discuss the concepts. Because where they went wrong, why the company has said this PCB cannot be manufactured, then what this PCB designer has done, whether they modified the design or they have told, no, you wrongly understood by what I originally meant for this and all. So this is what an important knowledge base. And let me tell you, this knowledge base has to be locally observed, with the local industry ecosystem, and you build it. And maybe you guys may think, sir, design rule means it's a very complicated rule or what? It's not a complicated rule. Most simple rules only. You have something called mill. Mill is one unit which refers to milli-inch. In the subsequent sessions, you will learn. That's a very small thing. Like, mill means a very, very small, much smaller than a mm kind of thing. A 1/1000 of an inch, you can understand a milli-inch, So if let us say one company says, I can only, take a PCB track, lowest of, let us say 4 mil. It means in your PCB routing, you should not take the track width less than actually 4 mil. It won't work. I mean, he can't manufacture. If you give that design also, maybe in computer, you can zoom in the computer and see, I'm able to see clearly and all. But the manufacturing technology, if their machine is not capable of doing it, so what might happen is in the process of getting the PCB track, if it is less than 4 mil, they're not very sure they're able to manufacture with the precision that you need so that your circuit will work. So the design rules are not complicated rules. They're very simple rules. But how do you program them at what stage in your design? And how do you do those rule check before you send it to the fabrication? This is what is only the learning element. So next one is, we talk about the file generation. So when you want to manufacture something, send it to the manufacturer. Then you have to generate the manufacturing files. So that also we are going to train you in this. We will take the popular industry in Bangalore and Pune and all and generate that. I mean, mostly they follow same file standards. Really, there is no confusion here. And even we have seen even the fabs in Singapore or Taiwan, Vietnam and all, they also pretty much use the similar file notion and all. Then next one is, once a manufactured PCB comes, immediately the hardware integration guys don't take. It is still the PCB designer responsibility. There are some test cases which are called, X-ray test report, BB, bare test report and all like that. You do all those point impedance checking and all those continuity checking and all. Some of the tests are done by the manufacturer and some of the tests you do because you are going to assemble onto that. Then you will send it to assembly. Then the assembled PCB comes, again you will do some checks and all. Once the PCB is proven with the assembled components, you will give it to the next layer in your hardware team, which are called hardware integrators. Then they will take it as a black box. They really don't know in PCB what is happening. You already taken care for thermal, you are already taken care for mechanical housing, stability, mounting holes, screws, nuts, everything you have taken care. Their job is to fix as per your guidelines, connect the input wires, connect the output wires, and use them in their system. So then last important thing is manufacturer selection and documentation. So we want to go deeper into the defense and aerospace documentation standards. And it is more important to understand because once you make a design, it must be approved by the military bodies. And they ask some test cases. So if you are aware of that, then you become readily, working man or woman in a company. So we want to even train on that aspect also so that you become capable enough to get a job very easily, saying that I know everything right from design, qualification, standard certification, talking to vendor, understanding the challenges of vendors and all that. Okay, so my remaining part of the presentation is just to give more insight of it. So I believe more in face-to-face conversation than this. So this all material, whatever we discuss, understanding the terminology, we talk something active, passive. Active is, you have some gain, BJT, MOSFET, these are active components and all. Resistor, capacitor, inductors, these are all passive components. So netlist is nothing but a particular text description of your schematic or a layout. Okay, it is a computer generated kind of thing. Some of you might have used the SPICE coding and all, so netlist will be something similar to that, but mostly netlist is your internal use. Gerber is something which you go to manufacturing. So Gerbers usually are nothing but layer by layer, where you are going to put metal, where you are going to you're open up for the metal, where you put your solder mask. Solder mask is nothing but their soldering should not come. That's a point. So where soldering is supposed to come, solder pad it is called. So all that will be there as a layer by layer information in your Gerber file. So you learn more in subsequent courses. Schematic and layout. You already know about schematic. Schematic is where BJT symbol, connectivity and all you know. Layout is all the physical, like you see this one, the metal layer, via and all. Then you should know the design for testability and design for manufacturability and all. If you design something, if it cannot be tested, then also your design is a poor design. You design something and the manufacturer finds a yield-wise problem. Let's say you ask him to manufacture, he makes 4 attempts to make correct design, then there is something wrong. You are happy that manufacturer is still working with you. Otherwise, manufacturer will say, no, your design is not DFM qualified, so I cannot manufacture your design. Because you are asking too many stringent things, too many complicated things to be done. And considering the tolerances of the manufacturing equipment, the most of the designs will fail. So application requirement. So this already we discussed. So what is your application? What is the exact functionality? By end of the day, any design that you are making should serve some purpose in a bigger system. So that is the most important thing. Here there is a multi-dimensional learning you need. You need to learn about the constraints. You need to learn about size, weight, power constraints are there. You need to understand the packaging, like any metal corner only you have to do, or can you make a square PCB, a rectangular PCB, or if sometimes what happens, the missiles and rockets, they have cylindrical shape. So people expect you to make a cylindrical PCB like that. So all those mechanical, size, weight, power, functional, all that you have to understand about the requirement. So this itself is an important thing. Yes, this is a complete design flow of that. So our people will go much detail in when they are discussing. So this is schematic design total flow. So I'll not go into details now. So when you are making the selection of components, see sometimes what happens, the same Zener diode may be available for 10 variants are there. You should know really what reverse breakdown voltage is important for you. From the what is actually coming here. One Zener diode whose reverse breakdown voltage is maybe 60 volts or something, may be very big and bulky. Actually, you don't need it. In your application, you're not getting more than 6 volts or something reverse breakdown voltage. So you'll be happy to take that one. So if you know what is the stress that is coming on each component, either it is a stress or it is an application-wise requirement coming to each component, that your choice of a component becomes very easy. But as I said, 90% of the times you go with the standard designs. Okay, now this is how when I say PCB backend, this is how it looks like. You can see the image here. So wherever this green is there, it has some significance. Wherever this is there, this is a metal line which is routed, something like that. So you will learn more about it. But if you look at this PCB at a microscopic level, okay, you see like this. So this is the top layer, this is the bottom layer. This is called via from the top to bottom layer, and you have routing done in a different layer. So top layer, inner layer 1, inner layer 2, and all they called. So there are some terms which are popularly used called pre-peg. That is nothing but the dielectric material that you use in this one. So I mean, how it is actually manufactured also, they take one layer and all, they press it, something like that. So more about this, there are a lot of YouTube videos are there. You can learn how this multi-layer PCB is done. So coming back to the skills that are associated with it, you should learn, again I said, design rules are what is a manufacturing design rules. If a manufacturer says I can make up to 16 layer PCB, but I can only support your intermediate layers of this type of pre-peg, which has got this type of this value of epsilon r, you should consider the same in your tool. Otherwise, you design, but he says I can't manufacture your PCB. So first, this is called stack up. Stack up is a word popularly used in the industry, communication between PCB manufacturers and the PCB designers. It is a PCB manufacturer will give the stack up constraints and everything. You put those stack up in your tool, whatever tool it is, then you do your PCB routing. Obviously, any design rule check, if you have modeled all the design rules also, constraints also, wherever the rules are violated, tool only will tell you the first, then modify your design. If there are no design rule errors on the stack up, then if you give this to manufacturer, he is guaranteed to give a working PCB on that, or provided your design is taken care. For example, he is guaranteed means, see, for example, you have put this PCB track. You can see this is a top layer PCB track. This is a top layer PCB. There is a wire that is coming here. This wire which is coming will act like a lumped, parallel capacitance which is coming over here, because our capacitance or inductance and all, we'll study all of them. Some component which will either create a phenomena of basically a low frequency or a transient kind of thing. So if you are thinking that you are running a 100 megahertz signal track on it, it may work. But the PCB manufacturer do not know that whether you want to run 100 megahertz signal on it or 200 megahertz signal, 300 megahertz signal, it is a sine wave or it is a square wave. The manufacturer do not know. But what you have to do, which is called signal integrity analysis, it is a mechanism by which you will be able to extract the electrical equivalent, the netlist. So the schematic originally has got only BJT and resistors in the emitter leg, but since there is the emitter leg also has got a via, the associated inductors or capacitors which are coming up they are extracted by the tool, and that if you simulate, there you will see your square wave of 400 megahertz is still going or not. So this is all done usually as a signal integrity analysis. So depending upon your PCB complexity, you may take a call whether to do signal integrity or not to do. Okay, sometimes you feel not required. I am pretty much aware of the standards. Anyhow, my design is only 50 megahertz, it will work. So you may leave it like that, or you may do signal integrity analysis. So library creation is nothing but, mostly commonly used components, their circuit symbols, their footprints, their like how they physically, footprint is nothing but on a PCB stack up how it looks like. For example, you see a lot of the places where you are going to solder a component, footprint is nothing but exactly how the chip is going to land, showing the soldering area. That's called footprint. So these are the symbols creation. In fact, in our company at one point of time, our projects got choked just because there are no people to create footprints reliably also. So that somebody who is experienced also may have to create footprint. So every role, every skill that you pick up has got its own importance in the industry. A designer who is making footprint circuit symbols and all will be working across 10 different projects, but his reliable way of generating the footprints and schematic symbols with 100% accuracy or a near to 100% accuracy will enable all projects to go smooth. I have seen several projects. A footprint creation wise mistake will lead to 2 weeks of complete design cycle impact. Why? Because you created a wrong footprint, and that chip is that component is so many there, 30-40 places are there. Now the footprint, they realize it has come wrongly. You have not put enough solder mask or clearance for the solder pad to and all open up and everything. Now everywhere the small adjustments is asking you to reroute the signals and all, and it creates a lot of problem. And I have also seen the PCB itself goes for second iteration because the footprint designer has done a mistake. Maybe when Nilima takes up the case studies, she will show the examples. Okay, her team member or herself may show the examples. See, when you have to put the, a design for manufacturability is that only. Let's say when you have a PCB done, when tomorrow, let us say the component I am placing on it in a reflow mission or in a automatic pick and place soldering mission, if my soldering is not happening reliably because I did not give enough openings for the solder to sit and all like that, then it is not a DFM design. So I have seen at least in our projects, there are 5 to 10% of the PCBs will go for second revision because the footprint did not come correctly. So it's a very important role and it's very easy to learn. Okay, the PCB layout workflow. This is about the PCB layout design. So maybe I already covered these things, that the constraints, track widths, clearances. Okay, then bends. You cannot take a track just with a bend, 90-degree bend and all. So there are some issues are there. So you will learn more into signal integrity. You will take a curved bend and all. So that curved radius also, there are rules are there, frequency wise and all. So you will learn all of them. Okay, so in layout design, you have different things like where to put a via, where to put. Now this is a through hole via, which is connecting top layer to the bottom layer. This is actually called blind via, which is coming from either the top to bottom to one of the inner layer. Buried via, it means actually, it is buried inside the top and bottom. Somewhere between intermediate layers, it is giving connectivity. So when you are doing such a design, you definitely know within this buried via, you cannot put any probe or any measuring mechanism and all. So you will cautiously do a design where I need an access points, what I can afford to be blind via, what I can afford to be buried via, where I cannot afford the through hole via because it's going to have a lot of parastics added to my design. My clocks will slow down, my frequency response will fall. So you have to take all those decisions. And when it comes to the power supply routing, power and ground plane routing, that itself is going to be a deeper subject. Okay, if you become good at power and ground plane routing, most of your interference aspects you will be able to handle easily. And good ground plane is very important, and in RF designs. In RF, I think most of you might think, see, what you have to understand is at low frequencies, it doesn't make difference whether you talk the signal is passing through the track or signal is passing between the two tracks in between dielectric, like what we discussed in our electromagnetic theory, that in a waveguide, the signal will travel between the two metal surfaces. Okay, TEM mode or something. At low frequency, it doesn't matter. But at high frequencies, the signal will travel actually in the dielectric only. So there is a signal layer, there is a ground layer. The signal is traveling in the dielectric. Okay, something similar to the wireless signal that is traveling in free space or air, that your telephone signal and all. Only difference is this is air with a dielectric constant of 1, epsilon r is equal to 1, and the impedance, the free space impedance is becoming 120 pi, I think the 377 ohm or something like that. Whereas if it is a PCB where you are talking about a dielectric constant of maybe depending on material Rogers or type maybe 3 or 2.2 or something, and there as a standard we design for 50 ohm impedance with that. So at high frequency, the signal is actually traveling in the dielectric medium between your ground plane and your signal track. So if your ground plane is not properly given, so then high frequency RF PCB design and all, it goes to 6R, it won't work. So these are all important things in the layout design. So in the advanced layout design, you talk about the crosstalk. Signal integrity, I already explained. What is the interference one on the other end, like that, the crosstalk. Thermal management, as I mentioned, becomes very crucial. And let's say in our company, we have 20 plus people working on this. There are only 2-3 people who know how to speak to mechanical guys. So you can understand how crucial it is. So you should be able to read the data sheets of the devices. You should be able to understand what is the law of conservation of energy. So if energy is coming as an input, energy as a going as an output, then rest is dissipated in the form of heat only. So that heat, how much is the heat? And there are the resistances between your junction to the casing and casing to what is called packaging, like that you have resistances and all. Then you with those resistances, you will understand how much thermal conductivity is possible from the die to the surface of the chip, and what type of heat sink you have to attach, and whether it is a airflow design, I mean like air cooled design, or it is a liquid cool design. All these matters, and that is where the real challenge I see. So in a company where you have 20-25 designers, only 2-3 people are able to talk all this. So you can understand how complicated they are. But if you ask whether they're really tough, I don't say they are tough. If you are good at few basics, simple basics, you will be able to do 90% of the job accurately. So then next about the power analysis and distribution. So you will be doing power analysis, ground analysis and all that. Ground planes, high speed signaling, I already mentioned about it. Then thermal manage, this is what I mentioned about. So you have basically there is a PCB here. This is what is a component, but if you go inside the component, there is a die here. So from die to the packaging, there is a resistance. From the packaging to the PCB, there is amount of thermal resistance. So based on that, you will be actually able to, I'm sorry, you will be able to pull out the hot spots. And from those hot spots, you have to design heat sinks. So from the surface of the chip, then you will be actually from the surface of the chip, you will be coupling to the air. So again, there is a resistance coming up between this heat sink, to the air and all, depending upon the air flow. So you maintain more airflow, the resistance is less. It becomes it cools fast. So all this is done by mechanical engineers, but you should know what is the language to speak to the mechanical engineers, that we are going to train you. Then next, this is a continuation of that. So this figure is showing that how crucial is the thermal design. So you have to closely work with the mechanical people for two reasons. One is rigid fixing. You want your design to be very rigid and strong and all. Then second is you want proper thermal management is done. These two reasons will make PCB designers speak to the mechanical designers, and both should work as a team. So DRC, we already discussed about it. So you have a lot of rules to be done, and this is to ensure DFM, design for manufacturability. Some of the DRC is even to take care of signal integrity. Okay, the full DRC I'm not talking, I'm talking simple examples. Even signal integrity rules also we put in DRC only. Let's say there is a high frequency design. I don't want any sharp bends like this. I want a smooth curved bend like this. So that's also you can model as a tool wise rule and see if the rule is getting violated, tool will alert you. So this is about, we discussed, when you have to talk to manufacturer, you have to talk in some standard files. So Gerber files, drill files, assembly files and all, bill of material. You have to give some stencil which is a printing on that. Okay. You will learn enough case studies. Don't worry. By end of this course, you will be able to speak to any global PCB manufacturer to get your design manufactured. So then you will be doing about how do you select manufacturer? Also, there is internally we have a case study. So we'll discuss with that. Then post-manufacturing testing. So through one of the course, we'll show you through video. Like we will take you to the actual bench where they do bare board testing, where they do assembled board testing. Through video session, we will show you. I think the course instructors must be planning a visit to our factory also at an appropriate time. So that also will help you to get a deeper insight. But through videos, you will be learning a lot of things. Yeah, that's it. So hope I could give you a bigger picture in terms of the skills that is needed. The all skills that when you want to get a job in this area, somebody has asked what is a package that you say package is in your hand. You get a 30 what is it called 3 lakh per annum, or you want to talk to 12 lakh per annum or 18 lakh per annum, depends on your skill sets. If you only know how to make footprint and do a digital PCB design, you will be given 3 lakh per annum only. If you are capable of doing, let's say, RF PCB designs, also understand how to do printed antennas on that, at the same time mixed signal design, you may be offered 12 lakh per annum or 18 lakh per annum also. So industry has a strong necessity of actually having, every manufacturing industry, electronic industry has a necessity of having the PCB designers with these skill sets, no doubt about that. And this course is going to definitely make you familiar with all this. We'll give you assignments at most of the places where the skill only is possible to build with the doing kind of thing, practical kind of thing. You will install some open source tool as per our instructor guidelines. You will do small PCB designs. Okay, and some of the selected PCB designs we may also sponsor for sending it to manufacturing and getting it tested. So you get a feel of it. Then through our video lectures, whatever is happening in our company, we will show you, we will educate you, we will train you. And we will make you qualified engineer in the defense and aerospace 5G telecom industry, including the industry standard wise, including the concepts and standards in which you have to speak to manufacturer. Now it's up to you to show your determination in completing this course and completing assignments in time and make a strong career. So I will be happy to answer any questions you have. Yeah, someone said that if courses are going online, how do you do practical design? No problem. You will be installing the tool on your computer and you will be creating the assignments. And I'm telling you that you can email to the manufacturer and he'll be making the PCB. So there is no real limitation because this course is online, because it's a computer based design. Had it been a physically with hands, if you have to learn, if a soldering course is there, I cannot offer online. But this is perfectly possible to do online course. Except that I told you that touching holding the PCBs with your bare hand and doing some testing, which we have to show through video and all, but otherwise remaining everything you'll be learning. So what are the roles in PCB design? Yes, there will be an appropriate session where at least in Unistring, what are all different roles, but you have mostly like footprint schematic symbol creation people whom we call as the electronic component analyst. You study the components and all. Then we call a PCB front-end designer whose job is only up to circuit and schematic and all. Then PCB layout engineer, we call it a PCB back-end engineer who is doing the routing and all. Like that, we have 4 or 5 roles in our company. They will be discussed in subsequent sessions. Is it possible to learn completely understand all these new things in 12 sessions period? May not be. What is expected here is definitely this is not a spoon feed kind of course. We expect you to do a lot of reading on top of what we tell. So, but as needed, the course period may extend also. I think 12 sessions, I'm not really sure what it may extend sometimes to 15 sessions also. We are more goal oriented than the time bounded. So we don't have semester, we are not accredited to any university and all. Yes, we have certain stipulated period, quarterly training program, but yes, as needed, we'll stretch it. So is there any chance to join in RTL? If it is possible, I'm interested in VLSI. I think this question privately our moderator will take. Lavanya, Saistri may note down the Lavanya is a team member. She'll be able to answer. So we've gone through the design rules and design flow VLSI through our academic. Is there any relation between VLSI and PCB? Yeah, I already clarified that. VLSI backend and PCB design has a lot of similarity. That talks about metal oxide semiconductor level, like a silicon dioxide layer. You create a diffusion layer and all. That level of freedom you don't have at PCB design. But once you leave that metal layer and all, on top of that metals, routing, parasitics, understanding the design rules, there you talk about the design rules of a fab. A fab says, I can only make 90 nanometer design, so on, so by CMOS processor, something like that. So they are the design rules there. Analogy of that in the PCB industries, the design rules are like, you will say that my metal layer cannot be more than of 2 mil or 4 mil track width, like that. There is some parallel analogy is there. Circuit design concepts remain same. Circuit simulation concepts remain same. But there are different things. VLSI backend and PCB design. What all topics we should focus on the entry exam to grab the course? Yeah, you need to be good at components, whatever the basic component, resistors, capacitors, diodes that you have done, circuit theory, EDC and all, and some and a few questions on transmission lines. If Dr. Vishnu is in this call, he may be, I think he has created a question paper, he can answer that. Okay. And there is no secrecy here. In fact, when we actually put the question papers are also on the website. So if you feel that you missed this course or your friend has missed this course or someone and you are not able to do well, no problem, you prepare well, again reappear. Okay. So yeah, somebody asked about the bond period. Our HR will personally answer you that. Usually for freshers, it will be 2 years, but anything change, they'll tell you. I hope I answered all the questions.
Last question, sir. If we complete this PCB course, that will cover physical designing of VLSI.
No. If you want to do physical design of VLSI, do physical design of VLSI.
Yes.
Okay.
So I think we have answered all the questions. Thank you, sir. Thank you very much.
Yeah. Thank you.
Thank you, sir. Thank you very much for being on the panel today and
Wish
also
you all the best. Thank you, Saistri. Wish you all the best to all participants. And I again thank the panel members for giving their deep insight. In spite of your regular working day schedule, okay, you could give some insight to our students. Let's hope we together make strong nation. And if some of you join the defense, aerospace or Indian private industry, the productivity of the country increases, the GDP increases, and overall the country will see. We slowly become self-dependent. Reduce the import component from the foreign industry, and we make and rather send export. Thank you all.
Thank you, sir. And